Hello everyone, Assalamu alaikum. Good day to all of you. Today I, Jorina Akhtar, and my group partner Saiful Islam are going to present our research work which is entitled as Analysis of EEG Signal Classification for Application in SSVEP-based BCI using Convolutional Neural Network. Before going to the presentation, I would like to show the outline to the audience to make it more comfortable and friendly. These are the topics which we will be discussing along the way in our presentation. Now I would like to discuss about electroencephalogram, steady-state visual evoked potential and brain-computer interface. So what is electroencephalogram? Electroencephalogram or EEG signals are measurable expression of electrical activity of brain which are picked up by the scalp. These signals are non-specific signals. On the other hand, evoked potential are very specific and triggered. So what is evoked potential? Evoked potential is such kind of electrical signals that measure from the scalp after stimulation observed by the external stimulus. Corresponding to various stimuli, evoked potential are distinguished as visual, auditory and somatosensory. SSVEP or steady-state visual evoked potential is the part of visual evoked potential. So SSVEP are signals that are natural responses to visual stimulation at specific frequencies. This potential elicited by the change in visual field with the frequency higher than 6 Hz that can be detected from the occipital area of the brain. On the other hand, brain-computer interface is a hardware and software system that establishes the direct communication and real-time interaction between a human brain and external devices. This slide is about the problem statement. These are the following major problems which are discovered. There is still a scope for improvement in accuracy, not much exploration on CNN-based classification. In slide number 5, I would like to discuss about the related works. Basically, we reviewed a lot of papers which are related to the SSVEP-based BCI as well as CNN-based classification. Among them, these two are the main one, which are followed by us. After reviewing these papers, we got that some authors got the highest accuracy, which is 79.47% while using SVM, which is a machine learning algorithm where feature extraction, feature selection, signal preprocessing had to be done before classification. On the other hand, some authors got the highest accuracy, which is 69.03% while using CNN classifier where raw signals are used directly to the classifier. In our project, we use CNN classifier for the classification purpose, and we did the filtering from 5 to 50 Hz frequency range, and we got the 69.7% accuracy by considering lead one subject out protocol and achieved 80.83% accuracy while trained the system by 70% of the whole data. These are the two major questions which arise in our mind during our research work. One is can CNN help to achieve better SSVEP BCI performance? And another one is, will tuning the parameters of CNN result in an optimized structure to achieve better SSVEP BCI classification? These are the main objectives of our proposed system. One is to analyze SSVEP signals for BCI application. Second one is to use CNN classifier. Third one is to improve the classification accuracy by tuning the parameters of CNN. And the final one is to compare our results with related works. This slide is about the outcomes and impacts. Our proposed system, which is SSVEP-based BCI, can be applied in wheelchair control or any other application, neural rehabilitation, word and letter recognition, digital gaming application, as well as biometric authentication. We can also say that our proposed system can keep a positive impact on these areas. Now I would like to discuss about the research methodology. For our project, we downloaded the database from PhysioNet, which is the Mamen SSVEP database, dataset experiment 1. Then we did the segmentation, signal preprocessing, spectrogram classification, final output, and we kept the main contribution of tuning CNN parameters. Now I would like to discuss about the database description. In database description, I would like to mention two things. One thing is that during data recording, 11 subjects are participated. Each subject has identical 5 sessions and 23 trials, and the total numbers of trials is 1,104. Another one is EEG-based 300 device has 256 channels. Among 256 channels, 40 channels are identified for the occipital area, which is our main concern because only occipital area of the brain allows us to investigate the classification performance of the EEG signals. Among 40 channels, 15 channels were experiment for our project, and among 15 channels, we choose only one channel, which is 138 number channel for the rest of the present for the rest of our project. Thank you. Now I would like to request Saiful Islam to continue the rest of the presentation.
Thank you to our partner, Joyna Akhtar, raw SSVEP sample and a spectrogram. As we can see, the signal in time domain is very noisy. While we convert the signal in frequency domain, we can see there are spikes at 50 and 100 Hz due to power line noises. So we had to filter out these noises. After filtering the signal, we converted the 1D signal to 2D images through spectrogram. This is our system architecture. The image is fetched into the system as RGB input and passed through several layers such as convolution layer, batch normalization layer, ReLU layer, max pooling layer, and then there is fully connected layer and softmax layer for classification purposes. The system updates its parameter by loss function. When the system gets an input, it predicts an output and compares the output with an actual value to determine the loss so that it can update its hyperparameters such as weights, kernels. And this process continues until the system reaches global minima point. Overfitting and underfitting. Overfitting happens when the validation loss and the training loss moves apart from each other. Underfitting happens when the system cannot reach the global minima point. And to overcome the overfitting, we can use drop factors. We have executed our experiment with several simulations. One of the simulation was for channel selection. We have considered 16 channels from occipital region, and channel number 138 gave us the best result. In pre-processing, we have used different frequency bands to filter out the signal. We have also used notch filters. 5 to 50 Hz, while we used 5 to 50 Hz frequency band, we have got the best result. While converting 1D signal to 2D images, we have used several configuration of spectrogram, but the default configuration of a spectrum gave us the best result. Convolutional layers kernel. This is actually the filter size and the number of filters. It has impacts on the validation accuracy. So we have considered different filter sizes and number of filters, but the best result was for 2 into 2 number, and the number of filter was 16. Multiple convolution layer. In CNN, we can use multiple convolution layer to layers, and in this experiment, we have taken several convolutional layers, but single layer gave us the best result. Solver, the optimizer, which helps the system to reach the global minima point. There are several slow solver, and this experiment was for RMS prop, root mean square propagation. The best validation accuracy was 78.96 with drop factor of 0.2. This experiment was for another solver, ADAM, adaptive momentum estimation, and the validation accuracy for this experiment was the best validation accuracy was 79.38 with drop factor of 0.001. And with another solver, which is SGDM, stochastic gradient descent momentum with momentum. While we executed this experiment, we have gotten the best validation accuracy, which is 80.83% with drop factor of 0.2. LOSO, leaving one subject out. In this experiment, we have trained the system with 10 subjects and test the system with 1 subject. And the result was, the mean accuracy was 66.65. This is the same experiment, but with different filter size and number of filters. And while we used drop factor with LOSO experiment, we have got the best result, best mean accuracy, which is 69.75 with HGDM, drop factor of 0.2. Conclusion. The complexity of designing a general model for airplane is very high, but it is suitable if the user takes the initiative for pre-training. We have got 80.83% validation accuracy with HGDM and drop factor of 0.2, while trained 70% of the whole data, and achieved 69.75 in our LOSO experiment. future work direction, trying different filtering pre-processing, and execute low experiment with different solvers, and also experiment with our own generated data, so that and afterwards, after getting the best model, we will be trying to implement the model in hardware. Selected references, acknowledgement. Any questions, comments, or suggestions? Thank you.